Example 8 says this: consider the diagram at the right for the next 3 questions. The diagram depicts initial and final velocities of an 800 kilogram car in 2 different collisions with the wall. Looks like in case A, we come in at 5 meters per second, we bounce backwards at 4 meters per second. Looks like in case B, we come in at 5 meters per second and we come to rest. We stop, we smash into the wall and come to a stop. So in case A, the car rebounds. In case B, the car does not. In which case, question I, does the car experience the greatest momentum change? A, B, both the same, or I need more information? You know what? I think we're going to vote. Again, how high you hold your hand up is how sure you are of the answer. So who says case A, Mr. Dueck? I think case A experienced the biggest momentum change. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, case B, the car comes to a stop. 1, 2, 3, 4, 5. No, both the same, because forces something, something. 1. Need more information. You know what? Let's just crunch it. Now, here, I don't think I'm going to use change in momentum equals force times time from your, because I noticed they gave me 2 different velocities. Jackson, from your formula sheet, which is the change in momentum version that has velocities and masses in it? Yep, that's the right equation. It's 3 and 1. Which one of those has the one with masses and velocities in it? Except instead of writing m delta v, I usually write it as m v final minus m v initial, because delta v is change in, what's change in anything? Final, see it, minus initial, see it? So m v final minus m v initial. Okay, get out your calculators. Jackson, what's the mass of the car? Okay. Times. In situation A, what's v final? And then minus, what's the mass of the car? 800 times. In situation B, what's v initial? Can't be 5. That's impossible. Okay. In situation A, Jackson, we have a change in direction. You let the 4 be positive, which is fine. So you let left be positive. So which way is right then? So times negative 5. Okay, and that's what you're going to have to very carefully watch for in this unit. If you see the word rebounds or bounces off, that means there's a change in direction. Cody, you need to let one way be positive and one way be. So in situation A, I get an impulse of 7,200. What about in situation B? 800 times, Jackson, what's V final? Probably could have skipped typing that, but I'll put it in there. Minus 800 times what's V initial. Again, if we're going to be consistent, negative 5, if we're going to use the same direction. Ooh. Which one had a bigger change in momentum? A or B or both the same? Very clearly A, because of that change in direction. In fact, the change in velocity in B is only 5. The change in velocity in A is 9. So let's circle case A. Question 2. In which case does the car experience the greatest impulse? Lauren. Too slow. Davin, in which case does the car experience the greatest impulse? Same answer, because Lauren, impulse is the same as change in momentum or momentum change. That was all it was asking was really, I was saying, have you remembered that impulse is another word for change in momentum? So case A. Oh, we answered part 3. What was the magnitude in case A? 7,200. Yes? Because you had to let one way be positive lean and one way be Negative. Okay. So now that you know what we're talking about, now that you're keeping an eye out for rebounds, let's look at the next question. Oh, yeah. What type of collision is worse for a passenger? Let's assume the initial velocities and the time of impact are the same in each situation. What's worse, a head-on collision where the two cars stick together, come to a stop, or a head-on collision where the two cars rebound apart? Nate, you just said it. First of all, what was your answer? I agree with you. Rebounding apart, much worse. Why? Okay. So, rebounding has bigger impulse. I would start with that. Wait a minute. What's a better way to write impulse? Delta P, that's less writing. Okay. Now, who remembers? I've mentioned this a few times. What actually does damage in car accidents? It's not the force, the acceleration. So really we want to ask which of these, why would this lead to a bigger acceleration? Well, bigger impulse means bigger F times T, because that's another way to calculate impulse. Did the question say the time of impact is the same for both? Well, if you have a bigger impulse but time is the same, what had to get bigger? This is what you were saying. Yeah. So force increased. D naught F equals what? Well, did the mass of the car get bigger? No, but the force got bigger. That means acceleration increased. Yeah. If you watch tackling sports, by far the biggest collisions are where they run in and bounce off of each other, not where they wrap each other up and come to a stop. Example 10, the diagram below depicts the changes in velocity of a ball that undergoes a collision with a wall. Indicate A or B, which one has the biggest change in velocity, biggest acceleration, biggest momentum change, biggest impulse, and support each answer. So for supporting each answer, I'm going to do my work down here. It says greatest delta V. What's delta and abbrev for? And what's change in anything? From your formula sheets, very first thing I gave you, but that's one that's worth having in your brain. Okay, so the change in velocity is going to be V final minus V initial in both situations. The change in P, change in velocity is going to be V final minus V initial. Okay. Jada, in case A, what's V final? I can't hear what you said. Okay, you have just decided that left is positive. That's okay. I'm fine with that. Doesn't matter. In fact, I would kind of do that as well, and I'll show you why. So it's going to be that and then minus. What's VI? Don't say 10. What is it then? The reason I might have made left positive, and can you see in the middle I get a minus minus, which is a, and I'm better at doing math with positive numbers in my head. So honestly, if I'm being sneaky, I'll often let final be positive and initial be negative, so I get a minus minus, which is a. The change in velocity is 15 meters per second. Okay. Ashton, what about situation B? What's V final? Let's use the same negative positive reference frame that Jada did. So V final is going to be what, Ashton? Positive 28 minus negative 30. By the way, can you see if you don't pay attention to the change in direction, you might say the change in velocity in case A is 5 and the change in velocity in case B is 2. It's a really easy mistake to make. Don't do that. The change in velocity here, 58. Is that right, I think? Okay. So which one has the biggest change in velocity by a long shot? Hannah. Explanation that we calculated it. Which one's going to have the biggest acceleration? Well, acceleration is change in velocity over time. That's a vector sign above that, Mr. Dueck. Very messy. Hannah, which one had a bigger change in velocity? Which one's going to have a bigger acceleration? Which one's going to have a bigger impulse or change in momentum? Which one's going to have a bigger force times time? Oh, wait a minute. That's another word for impulse, change in momentum. Yeah, definitely hitting a car. Again, if you don't have a physics background, Holly, it's really easy to say, no. Case B is only having a 2 meter per second change. No. There's a change in direction, and velocity is a vector. We need to let one way be positive and one way be negative. Okay. And yeah, Jada, even though you felt sheepish at first, saying, "Oh, I should let final because it's to the left be negative," I kind of often let final be positive, so I get that minus minus, which is you don't have to, but you'll notice in a lot of my answer keys I do that. Lazy but organized. Okay, your homework is going to be yeah, I think every question here. So I had already circled some. But first, this was made by some kids from Britain as their class project. I thought, it's a pretty good explanation of why we have crumple zones in cars. So look up.
I'm Nick.
And I'm Jane.
Today we're going to look at momentum and how we can use this to understand why we need crumple zones in our cars. Let's start off by looking at some theory on the whiteboard. Let's remind ourselves that momentum is equal to mass times velocity.
Yes. By the way, what symbol are we using for momentum? Can't use M, it's taken. What letter do we have to go with? P for product. This is not impulse. This is not change in momentum. This is just straight momentum. Davin, want to sit up? Thank you.
Mass times velocity. If our car weighs 1,000 kilograms and it is travelling at 25 meters per second, what is its momentum?
You can probably do that in your head. Going to be 1,000 times 25. What's its momentum? 25,000 kilogram meters per second. Okay.
That's right, you've got it. 25,000 kilograms meters per second. What happens when a car hits a wall? Because the car's velocity becomes zero, its momentum must change to zero during the collision. We can use the change of momentum formula to allow us to find the force that acts on the driver during the collision.
There's our delta P equals Ft. One way to calculate change in momentum.
Rearranging the formula, we get force is equal to change of momentum divided by the time over which the collision acts.
So what happens when time gets bigger? What happens when time gets bigger? What's going to happen to this answer of force? This is why all of our car crash safety is about lengthening the time of collision. Airbags, crumple zones, those big water or sand-filled barriers you see in front of cement barriers, like when you're approaching the pit bridge, those big barrels full of water. It's all, can we lengthen the time of collision? Here's the nice thing. Without any interventions, the time of collision is so quick, it's not that hard to double the time of collision, and you've just cut the force in half, dramatically improving the survivability of a crash.
Now we can use this formula to see how we can reduce the force on the driver. Because the change of momentum will be the same for any specific collision, if we increase the time, it will make the force smaller. Now we can put this theory into practice by looking at crumple zones in a real collision. Let's go over to our brave stunt driver, Ollie. Ollie, are you ready to go?
I think so.
So here's a car with a crumple zone. Now without a crumple zone.
Oh dear, I hope Ollie was okay after that second crash. Now let's go back to the whiteboard to see if we can work out the forces involved in those two collisions. So the car had a mass of 500 kilograms and a velocity of 10 meters per second. In the first collision, when the car had a crumple zone, the car and the wall were in contact for 1 second. So if we put those numbers into the formula, we can see we get a force of 5,000 newtons. Now let's look at the second collision. In this one, the car had no crumple zone. So the car had the same change of momentum, because it was still 500 kilograms, going at a velocity of 10 meters per second, but the contact time between the wall and the car was only 0.2 seconds.
The only thing I would say is technically both of these change in momentums should be negative because the car has to lose all of its momentum, but whatever.
So if we put these numbers into the formula, this time we get a force that's much greater of 25,000 newtons, which is why poor old Ollie ended up being thrown out of his seat. You'll be pleased to know that Ollie has made a full recovery and will be ready to do some more experiments for us next week. That's all for this edition, so it's goodbye from me.
And goodbye from me.
Pretty good explanation, actually. Okay. By the way, I said you could the final momentum should be negative, or you could do like Jada did and just let your final be positive, and you'll still get a positive answer as long as you're consistent in your frame of reference. I will mark you right. Just don't switch partway through. And Ashton, don't miss if there's a rebound or if there's a change in direction, because that's where I'll get you. You do have to let one way be positive and one way be negative. So shorter lesson today, lots of practice for you. Also, a number of you still owe me the homework from lesson 1 and 2.